All right, first question we got was, what does random.seed do? So random.seed basically makes it such that every time in that notebook or in that lab you're doing anything random, you get the same random over and over again. So let's say in the lab they want you to take, like, out of 10,000, they want you to take like a random sample of 100. For the sake of reproducibility of your experiment, because you set the random seed, and random seed takes, I think, any integer. Because you set that random seed, it's always going to take the same sample while you're doing your lab. I was actually talking about this with someone at a 101 today, but the way that computers and Python do randomness is actually a very interesting topic on its own. It's actually not purely random, it's actually pseudo-random. So if anyone's interested, you can take a read, possibly be a blog, I think. It would make a really good blog topic in my opinion. But yeah, so random seed basically makes it such that whatever you're doing in your notebook does the same sort of random. And it's for reproducibility. Any other questions? Awesome. Well, let's get started. This section sort of, interestingly, is titled hypothesis testing, even though we already saw hypothesis testing in section 12. This section is mainly going to be t-tests, and then we're going to talk about type 1 and 2 errors. So really quickly, the overview. We're just going to review the steps of hypothesis testing. We're going to talk really quickly about p-values, because p-values is one of the more important things. P-values are going to be the most common thing that you're asked to interpret, I think, at least for Mod 2. When we get to our Mod 2 project, p-values will be one of the most important things that you need to be able to interpret in your model. Then we're going to go on to effect sizes, and effect sizes in this mod is kind of a separate thing, but it comes back next section. So we'll talk about it really quickly here. We'll elaborate next section. And then the bulk of this presentation is going to be on t-tests. So here we have two new tests that we haven't talked about. We talked about the z-test, and then we talked about, did we talk about t-test? I don't really remember. The last test that we did was...
Yeah, we did t-test, right?
Yeah, all right, so we did a t-test, but we did it with confidence intervals, I believe. Yeah, that's right. We did it with confidence intervals. So here, more formally, we're going to go through the one-sample t-test as well as a two-sample t-test. So these are two different kinds of tests, and I'll set up each with their own examples, situations in which we'll use each one. And then finally, we'll end off this session with type 1 and type 2 errors. So type 1, type 2 errors, it's important to know type 1, type 2 errors in the context of false positive and false negative. I'll elaborate later. But yeah, actually, I'll elaborate on that later. I won't say any more. So all right, to start, this is our statistical testing process. We're going to be using these processes in our next two tests that we're going to go through today. So first, before you even start calculating anything, you're going to set up your hypotheses, and then pick the statistical test, pick your alpha, and then you calculate your test statistic, find your p-value, and interpret. So we're gonna take a little bit of a detour before we come back to testing. We're gonna talk about p-values. So a definition to remember is that the p-value is a probability of observing a test statistic at least as large as the one observed by random chance, assuming that the null hypothesis is true. So the assumption that the null hypothesis is true is something that we can't really control. If we're told that the population mean is something, we can't really prove otherwise. But the p-value is the probability of observing a test statistic at least as large as one observed. So basically, each test statistic, as we know, is associated with a p-value. So for the z-score, we can look up the probability, we can look up the associated p-value on the z-table. And later we'll see for a t-statistic, we look up that, each t-statistic has a p-value that we look up in the t-table. And what that means, I think it'll be easier to explain with context later, which I will explain as we go through the tests what the p-value means in that context. But p-value is a probability that something is observed by random chance, which is actually a very interesting concept to be aware of. Anything before we move on?
So when you say random chance, it's like it picks up automatically, or we need to specify in the data that, okay, this is the random value that we want.
So p-values is more used to, you would compare your p-value to whatever alpha you choose. I think it'll kind of make sense later, but let's say our alpha is 0.05. If we get a p-value of 0.6, that means that our p-value is larger than alpha, and that means that there's a chance that this statistic was more random. Was about, there's 6% chance that we got that statistic randomly. And so because of our alpha, usually we want p-values to be lower than our alpha. So alpha, in another interpretation of alpha, is like your threshold for which you can allow something to occur by chance. Does that make sense? I think with examples, and if I don't say it in context with the examples later, someone please remind me. But I think it'll be easier to understand in the context of like a problem that we set up.
Okay.
All right. So p-value, this is a definition that I would remember. All right, really quick, another detour, effect size. So effect size basically just measures the difference between two groups. So you can, let's say you have like a bunch of males and a bunch of females and you want to compare their heights. So effect size measures this difference, but not just in terms of like, all right, average height minus, and then get that difference, but it also takes into account population size and things like that. And so the most common one that we use is Cohen's d, and that's the name of the metric that you use to measure the differences between things. And so it measures it in terms of standard deviations, and it's measured from 0 to 1. And these values of 0.2, 0.5, and 0.8 being small, medium, and large, these are just like rules of thumbs. So typically, when dealing with something like Cohen's d, and we'll start to get more into it as we get closer and closer to our project, but a lot of these things are very subjective based on the thing that you're measuring. So these are good rules of thumbs, but if you find that, you know, if you're maybe comparing two groups that you have a hypothesis should be more different or more similar, and these don't really match up, then you definitely have space to use your own judgment. But effect size we will come back to on Thursday. So let's not worry about it too much here. I put it here just because it's in our section 14 learns. Which reminds me, I did not go through the learn labs for this section. Just really quickly, I think the more important ones here are definitely, these are all good to read. Definitely read like experimental design, p-values, and the null hypothesis. Effect size is a good one to read. Effect size, you'll actually see back here, statistical power, effect size is coming back in section 15. So I would just read that to get like a good primer. But the main labs for this section are the t-test labs and the type 1, type 2 error labs. Resampling methods, very interesting to read. Definitely read it if you have the time, but not a priority for this section. All right, sorry for that massive detour. All right, so let's get into our tests. So let's start with the one-sample t-test, which is very similar to our one-sample z-test, the only difference being that we don't have our population standard deviation. I think I mentioned this when we introduced the t-distribution, but as long as you don't have the population standard deviation, immediately you should think t-test. So this is our sample question. I took it from the lab. Acme wants to improve sales performance. Oh, yeah.
Can you repeat that? Like as long as
no worries. As long as you don't have your population standard deviation, you should always default to a t-test.
Oh.
So actually, t-tests are way more common than z-tests. It's just that, as you'll see, t-tests have more calculations to be done. All right, so in this example, Acme wants to improve sales performance. Past sales data indicates that the average sale was $100 per transaction. And then after training the sales force, recent sales data from a sample of 25 salesmen is shown below. So this is our sales data after they've gone through training. So based on this, anyone want to make a guess on like what the hypotheses will be? What our null and alternate hypotheses will be in terms of the average sale per transaction? Anyone? All right. All good. Our hypotheses, so going back here, it used to be 100, and our hypothesis is we want to see if sales performance has improved. So in that case, our null hypothesis is that, all right, mu is 100, and our alternative hypothesis is that mu is greater than 100 because we want to see an improvement. So it's a one-tailed test. So that's usually step one. Step two, step three, we know we're going to do a one-sample t-test. And our alpha is 0.05 as usual. And in a t-test, the things that you want to calculate and the numbers to note is keep track of population mean. So you have population mean, the number of observations in your sample, which in this case is 25. X bar is our sample mean. S is our sample standard deviation. And the degrees of freedom, I know it's kind of confusing because we've been working with data frames, but DF is actually, at least in statistics, DF is degrees of freedom. And degrees of freedom is 24 because degrees of freedom, I think of, as I mentioned last study group, is DF is always n minus 1. So whatever the number is in your sample, minus 1. So these are the numbers to calculate. So with all of this set up, next we're going to see the t-statistic. I needed to find a better way to display this information. But the t-statistic is actually calculated very similar to our z-statistic. We take x bar minus mu, so the difference between the sample mean and the population mean, and divided by the sample standard deviation divided by the square root of n. And this is a formula that you can just look up. And there's also a built-in formula, which I'll actually talk about the built-in formula with a two-sample t-test, but this is also built in. You can find it in SciPy. T-statistic is 3.5781. So when you're doing a t-test, this is just an excerpt of the t-table that I have in the background here. When you're doing a t-test, what you have to do now is look for your critical t-value. So based on the alpha that you chose, there's an associated critical t-value that you will compare your t-statistic to. So how you use the t-table, let me just actually pull it up so it's a little clearer. Let's go back here. So t-value table, this is that same table that I took. Is it the same table? I think it's a different table, but whatever, same thing. You look up our alpha, and our alpha was 0.05, and make sure you're looking at the correct one. So in this case, we're doing a one-tailed test, not a two-tailed test. So in one-tailed test, our alpha was 0.05, and then our degrees of freedom was 24. So we're gonna go 0.05 and look up 24, 0.05, look up 24, and our critical t-value is 1.711. So it's 1.711, which actually is similar to here. If you look up 0.5, and once this bar disappears, you can sort of see that where 24 is, 1.711. So this graph basically shows us the t curve. This is the t distribution. This green line is our critical t value. So you can see this is sort of like 1.711. And then this red line is 3.57, which is way right of the critical t value. Therefore, we can safely say that this T statistic is, the T statistic here being greater than 1.711, we can safely reject our null hypothesis. And so therefore, that training really worked. Questions? Because this is all for a one sample t-test.
Could you go over alpha again?
Mm-hmm. So alpha is your critical value. And alpha is something that you state at the start of the experiment because you don't want to be biased by any results. So typically you always choose alpha before you even like calculate any values. And so alpha is typically set at 0.05 just because that's what I guess people in different experimental realms use. But alpha determines your one, it can be used to get like a critical value of like where you actually reject or fail to reject your null hypothesis. Alpha can determine like your rejection regions. It determines like how wide your confidence intervals are. So alpha is just something that tells you basically how strict your test should be. So in this case, our alpha was 0.05, and it gave us this green line over here. So basically, anything to the right of the green line, you would reject. So if you want your experiment to be more strict, you would actually set a lower alpha. And once again, alpha being 0.05 means that this area here, this blue shaded area is 0.05. If you want a stricter test, you would set a lower alpha. So let's say you do 0.01. This green line would be shifted to the right, such that the blue area is 0.01. That way, it's even harder to reject the null hypothesis. It's even harder to get, like the chances of getting your red line to be to the right of the green line it'll be harder to get a red line to the right of the green line as the green line keeps moving to the right. If that makes sense. So actually, yeah, at an alpha of 0.01, let's actually take a look at what the critical value would be. So an alpha, a one-tailed test, 0.01 here. So this column, and we scroll down to 24. So at 24 degrees of freedom, our critical T value would have been 2.49. And so 2.49 is actually still less than 3.57. So I guess this training actually really did have a significant impact on those, what are they called? On the sales, on sales performance. Does that make sense? All right, so that's a one sample t-test. I think the labs have you go through two, like one in the reading, one in the lab. So that's a good thing to get exposure to, I think. All right, so now a two sample t-test. Lots of words here, but this is just the question that we're gonna set up. It is used to measure if two population means are equal. So this is actually very commonly used if you have like a control group and an experimental group. So let's say, I don't know, you have a new drug that you want to test. So, you know, you give like half the group a placebo and half the group the actual medication. You can use a two sample t-test to see if there's a difference in the way that, you know, in this example, we have blood pressure. So you want to see if like the medicine actually lowers blood pressure. So let's read this example. Control group and experimental treatment group, blah, blah, blah. And so researchers are interested in the average difference in blood pressure levels between the treatment and control groups. So this statement is actually very important. It doesn't seem like it, but it's actually really important because researchers are interested in the average difference in blood pressure levels. They didn't say whether the blood pressure levels will go down or go up. They just say difference. And these wordings are always, if anyone's ever taken like a stats class, these wordings are always what tells you whether it's a one-tail or a two-tail test. So because they didn't say whether they're looking for an increase or a decrease, because they don't say that, this is going to be a two-tailed test. And we'll see how the hypothesis is different later on. So
this even one tail, right, instead of two tail, because the difference is a single section, but then like when it is an increase or a decrease, there would be two different sections, right?
Yeah, so it'll be a two-tailed test. because it could be increase or decrease. Therefore, it's a two-tailed test.
Oh, this is an increase and decrease. Okay.
Yeah. So here if it was a one-tailed test, in the setup of the question or the setup of the problem, they would say something like, researchers are interested to see if blood pressure levels will drop when given the drug.
I got that. But I thought like we were only looking for a basic difference, not increase or a decrease.
Yeah, exactly. So because we're only looking for a difference, they don't specify which direction the difference is. Therefore, it's a two-tailed test because they don't specify whether it's higher or lower. So we have to look at both.
Okay. Yeah. Got it.
All right. Great question. Okay. So in this setup, control group, they have an average blood pressure of 121.38, and they got a placebo drug. And in the experimental group, they got 111.56 after treatment and after getting the actual drug. So it seems like, so this is just to set up the problem. It seems like the difference between each group is, between the two groups is 9.82, which you think, I don't know, in the context of blood pressure, I'm not familiar either. So I can't really say whether that is a significant difference or not. So we're going to use a two-sample t-test to see if the groups are significantly different, and therefore you can make a conclusion on whether the drug was effective or not. Got it? That was a lot of setup there, but yeah. All right. So lots of numbers going on here, but let's break it down. So on the top left, we start with our hypotheses. And the hypotheses here, a little bit different. You might see it in different ways. All right, let me just move this. You might see it in different ways, but the way that it is in the labs is that the difference between mu1 and mu2 is 0. Equivalent to this, you might see mu1 equals to mu2, but they're pretty much the same. The alternate hypothesis is that mu1 minus mu2 is not equal to 0. Got it? So in a one-tailed test, you either have like larger than or less than, but in a two-tailed test, it's always the null hypothesis being equal and the alternate hypothesis being not equal. Got it? All right. And in this case, yeah.
Yes, quick question. So I think it might be a little bit different, but when you described that, it just made me think about whether a distribution is normal or not. And so my question, because there's some like rule to determine, okay, this distribution is normal or it's not normal and everything. So when mu1 minus mu2 equals 0, that doesn't have anything to do with them being normal distributions, right?
Yeah, not at all.
Okay, just want to make sure. Okay.
All good. That's a good clarifying question.
Thank you. Okay.
All right, and so we have our hypotheses, and then we have our usual alpha of 0.05. And just to remember, it's a two-tailed test. And so this diagram doesn't really say anything right now, but it's just to show that, get this bar to disappear. It's just to show that we're looking at rejection regions or critical values at either side of the curve. All right, so on the right side of this slide, we're looking at the numbers to note and numbers to calculate. So this is actually taken from the labs. So the labs actually gave us all of these numbers. And we can see that, so the first line is the control group and the second line is the group that was given the drug. So here you can see that in the control group, the average blood pressure was 121.38, which I think, yeah, they said it in the question here. And there are 50 people in that group. In the second group, there are their blood pressure is about like 10 points lower, and then our number of people in the sample 50 as well. So that's what's given to us. For a two-sample t-test, there's a lot of calculation to be done. So this here is our t-statistic. T-statistic is the one that we're gonna calculate to compare to these rejection regions or critical t-values to decide whether we want to reject or not reject our null hypothesis. So I'm gonna kind of break this down or just like point to like what each of these letters mean. So T-statistic for a this is a 2-sample T-statistic, which is calculated using, these are the sample means. So X bar 1, X bar 2 actually would be the same as mu1, mu2. Here is actually a pooled sample variance, which is something I'm not going to go into as to what it means, but it's basically, simply put, is the variance of both of these groups together, which is actually calculated using this, but I'll talk about that in a little bit. And then pooled sample variance here, normalized by the number of people in each sample. So that's a T-statistic, which is calculated using this pooled variance. So this pooled sample variance is calculated using the standard deviations of each sample, which is S1 and S2, which are, the numbers are right here. You also use N1 and N2, and then that just gives you your pooled sample variance. These are formulas that when I was in college, I had to compute by hand, but great news, you guys don't have to do that. There is a lab that has you walking through coding out these functions, which I think could be good practice in like translating math formulas into functions. But it's kind of hard to interpret what's going on in the formulas by doing that. But anyways, numbers are here. When it's squared, it's a variance. So the variance for each sample, here I have 806 and 541. Plug these values into the pooled variance formula, got a pooled variance of 673.8, plug that into the T-statistic formula and we got our 2-sample T-statistic to be negative 1.891. All of these calculations, not super important. You just need to know that the values that you need are, you need your sample data and you need to know your, actually you really just need your sample data, because from your sample data, you can get the means, the number of things in your sample, you can calculate your sample standard deviation from that. There is a function built in to SciPy that does it for you and would pretty much straight up give you this T-statistic in like one line. So all you need to know is that is your T-statistic, and those are just some elements that make it up. Questions? I understand this slide is super math heavy, but just know that I'll show you the one-liner that can get you these values.
Is that different than the T-table?
This is kind of different from the T-table because this T-statistic is calculated. This is the T-statistic for your 2 samples. The T-table is what you use to get your critical T that you compare it to. Kishore, you were going to say something?
I mean, I just wanted to know about the function. So you said, right, you'll be just explaining the one-line function.
Mm-hmm. Yeah. It's on the next slide. All right, so our T-statistic is negative 1.891. I think our critical T values in this case are, actually, let's look it up. For 0.05 two-tailed test, so let's take a look at 2 tails, 0.05, and our degrees of freedom. Here, our samples are 50 and 50. So we're actually gonna look at, I believe we look at, because there's no 50 here. Reason being, I don't know if anyone's ever heard of, oh shoot, what's it called? There is a, basically if you have more than 30 in your sample, you can sort of assume that it's more of a normal distribution than a t-distribution. Don't take my word for it, but that's kind of why they stop incrementing every number at 30. But anyways, we're gonna estimate here. So here we're gonna estimate, it's between 40 and 60. So you can see that these values here, let me just double check, 0.05. Between 40 and 60 is about like between 2 and 2.02. And so in this next slide, our rejection regions are roughly plus and minus 2.0. And so anything inside the plus minus 2 region, we will not reject the null hypothesis. Anything outside of that, we'll reject it. So our t-statistic that we had calculated was negative 1.89. Very close, but didn't make it. So 1.89 being inside this, in between the critical t-values, means that we fail to reject the null hypothesis and the drug doesn't make a difference in blood pressure levels. So the drug didn't work. So this is the one-liner that I'm talking about. Stats, I think it's scipy.stats, so it'll be stats.ttest_int. All you have to do is feed it in your array of numbers for the experimental group and the control group. And then it will give you the t-statistic. So as you can see, we have negative 1.89. And with that t-statistic, it actually gives you the p-value of that t-statistic that we compared, that we calculated. So with a t-statistic of negative 1.89, it has a p-value of 0.0615. And if you remember what the p-value means, it means that there is a 6.15% chance that this happened randomly. And because our alpha was 5%, we don't want anything with a higher chance of being random than 5%. So based on this one line of code that gives us this output, we see that the p-value is higher than our alpha. Therefore, we can immediately fail to reject the null hypothesis.
Okay, question. Well, two.
All right.
So first question is, just to maybe to clarify, so you get the p-value of 0.0615 by using the t-statistic, is that right?
That's right, yeah. So every t-statistic comes with a p-value, which is hard, but it is something that we can't read from the t-table, which is why we have this. So that line there is just after you've used the t-statistic to get the p-value. Yes. So this first line is what you would code, and this line is actually the output.
Okay. So got it.
Yeah,
So
should have been more clear.
The output is going to be the t-statistic and the p-value at the same time.
Yep.
Okay.
Exactly.
Okay. Cool.
Yeah.
And then as far as I kind of forgot the question, but basically it was just related to the accepting and rejecting. So you said the alpha, if it's 0.05, but then the p-value is so there's 5%, for that one, but then for p-value it's at a little bit over 6%. Can you just explain a little bit why that's important? Yeah,
for sure. So on this graph, right, a p-value of a test statistic of negative 1.89 has a p-value of 0.06. So that means that the area under this graph until the red line, this bright red line, is 0.06. And so that just puts it in the region where we would fail to reject the null hypothesis. Does that answer your question?
A little bit, but I guess I'm just a little bit unclear as to why, if the p-value is higher than the alpha, that it actually you don't want that to be the case.
Yeah, because you don't want the t-statistic to have a high chance of having occurred randomly. Because let's say you have this if you get a t-statistic that is let's say -3, let's say our t-statistic was -3, that's good, right? That means that your drug really worked. But it still has some chance that was by off chance, all the people that you tested just had a really great reaction to this drug that is not that is not representative of how the drug would act on most people. So it could be that there's a tiny percentage chance that this drug just so happened to work so great for this sample. And so in that vein, in that like extreme case, there is a 6% chance that that this is the correct, that this t-statistic occurred randomly.
Got it. So then, see, and that makes more sense. But then, I guess my question is, does that mean that, like on one end, I feel like what you just said makes it more important to choose the right alpha?
Absolutely,
but,
absolutely.
But on the other side, it seems like what we've been discussing is that you can choose random alpha. Or no?
So you always want to decide on your alpha before you even calculate any statistics. You want to choose your alpha first. So that is sort of like, you're not hacking your alpha such that you will like pass your tests. It's sort of like, it's so kind of like
there's some thought process that goes into choosing the alpha is what I'm saying.
Yeah, just like generally it's 0.05. If let's say like, this drug is maybe like very, very expensive, maybe there's a lot of like side effects, you would want to set a more, you would want to set a lower alpha just so that, you're very, very sure that it works and that it's not working by random.
Got it. And got it. I understand now. So then, literally, that last thing really is like, 5% chance that it was random, right? So like 5% chance it was random. So if you want to be very exact, you would even take the alpha score even lower. So then that means the room when these choices are made based on this data, like it seems like there's very, very little room for it to be random.
Exactly.
So the more the more closer to accuracy you want, you will set lower alpha.
Yep.
Yeah, I guess not closer to accuracy. I would sort of think of it as like the more strict you want your test to be.
Got it. Yeah. Gotcha.
Like if you only want this drug to be released to the public if you're absolutely sure that it will work for everybody, and it would if you're absolutely sure that it will work for everybody, and that like this is not just like random coincidence that these 50 people reacted well to it, then you would set a lower alpha.
The t value and the t statistic and the p value, they're correlated, right? So you would never have like a p value that would be small or it'd be super large, and then a t value would be like on the other side of the line.
Yes, right? Exactly. Because the p-value is really the area under the curve. The p-value is always the area under the curve of this t-statistic. It's just that in the t-table, they don't give you that information. The t-table is different from the z-table. In the z-table, you can look up the z-score and it'll tell you the area. But in the for a t-table, it doesn't tell you that. So that's why we use we actually calculate the critical t's and then compare the t statistic. Whereas here, if we have the p-value, you can just compare area under the curve to area under the curve.
Got it. And that makes I'm not sure who said that, but that was a really important point, I think.
Yeah,
that was yeah, thank you, Henry, because like at first I was just thinking, okay, you just choose this random thing and then you just come up and then you compare it. It's like, well, what does it matter what I compare, what the comparison is? But because of that, now I understand that when I choose the alpha, whatever I get is not going to be too far away from it, but it's still going to show you something meaningful. Is that right?
Yes, because you're comparing either your t-statistic or your p-value to an alpha or the alpha's associated t-statistic, like the t that you get from your alpha.
Sure. Okay.
Yeah.
All right. Great. Thank you.
Yeah. So there's basically what I say is there's two ways to decide on whether you reject or fail to reject your null hypothesis. You can either compare your t-statistics or you can compare your p-values. T-statistics is easier when you don't have this one line of code, because you can just like look up the critical t's and compare your t-statistic. But because we have Python, we don't even need to do all that calculation. We don't even need the critical t values. We can just compare our p values here to our alpha. All right, any other questions before we move on? Because after this, we're going to talk about errors. Cool. The next slide is type 1 and type 2 errors. So just to set it up, in statistical testing, everything is based on a probability or some statistical significance, right? There are situations where we reject the null hypothesis when we shouldn't have, and vice versa. So there are type 1, type 2 errors. Basically, a type 1 error is exactly what I have here, when you reject the null hypothesis when you should not have. And the probability of your type 1 error is literally alpha. Because let's not care about this t statistic for now, but look at this critical value. The probability that you reject the null hypothesis when you shouldn't have is basically the probability of the curve of the probability of the curve to the right of that critical value. Does that make sense? So if this is your critical value and your probability of your, I guess, your t statistic being on this side of the line is the area under this curve here, which is usually 0.5 or alpha. So calculating this less important, just know that alpha is usually your type 1 error, but more importantly, it's a false positive. In this case, positive is when you reject the null hypothesis. I know it's kind of like backwards, but positive is when you reject the null hypothesis, and I guess in like, in words that you shouldn't say in statistics, you're accepting the alternative hypothesis. So that means there has been an effect on something. It's kind of backwards, but yeah. You're rejecting the null hypothesis when you shouldn't have, so it's a false positive. I think always just remember, type 1 error is a false positive. That's the main takeaway from here. Questions? Okay, so type 1 error is a false positive, and it's usually equal to alpha. Next, we have type 2 error. Type 2 error is the opposite. Type 2 error is when you fail to reject the null hypothesis when it's actually false. I know there's a lot of like negatives here, but overall, type 2 error is a false negative. And where the probability of a type 1 error is alpha, the probability of a type 2 error is beta. I know we haven't talked about beta yet. We haven't talked about beta up till this point. And beta will actually come back in the next section on Thursday, so we'll talk about that more on Thursday. But probability of a type 2 error is beta. And how it kind of works is that you're assuming the calculation of type 2 error sort of comes about when your underlying normal distribution has a different mean. And then the probability here is the probability that the area that you want to calculate for a type 2 error is up till this alpha point, but on this other curve. Why that is so is not important for us right now. But something that we're going to get to on Thursday is that the power of a test is 1 minus beta, and we'll talk about that on Thursday. But what I wanted to get at is there are two distributions here. This is H0 is our null hypothesis. That's our null hypothesis. And H1 is just some other distribution. What the other distribution is doesn't matter for now. But what I want you guys to see that is this dotted line is our alpha, is where we choose alpha. So these curves are static. But if we move the dotted line, so let's say we want to reduce our type 1 error. So we want to reduce the chance of a type 1 error. So we move the dotted line to the right. The blue area gets smaller, but the red area gets bigger. Does that make sense? So very often, and we'll see this a lot.
Is that always the case?
That is always the case, yes. That's always
Gotcha.
the case. There's some trade-off between false negatives and false positives. We'll see a lot of this in mod 3, but actually in mod 2, we might see it as well. Yeah, but more in mod 3. But there's always a trade-off between type 1 and type 2 error. like you usually want to optimize for less of something. In some cases, it's better to have false negatives. In some cases, it's better to have false positives.
Is it possible that like you are into exact center where like false negative and false positive are equal?
Yeah, definitely. But in most like practical applications, you would rather have 0 of something and a little more of something else. So for example, if you have like a medical test, let's say you want to test like a COVID test, you want to see if you have COVID. Would you rather be told that you have COVID but you don't? Or would you rather be told that you don't have COVID but you really do? Right? I mean, I think that it's better to be told that you have COVID if you don't. It's better to have false positives. Is that right? Yeah. Better to have false positives than false negatives, because you don't want to actually have COVID and just be like out spreading disease. So in that case, you really want to minimize your false negatives. You really want to get your false negatives as close to 0 as possible. And if that means that you have some false positives, so be it, right? Like some people just being extra cautious and like quarantining because they think they have COVID even though they don't. That's much better than the alternative. Yeah. So this is definitely something that you all have to start thinking about, especially when you're doing your projects. I think less so Mod 2 project, but more so Mod 3 project. You'll see why later. But whether you want to hire alpha or beta really depends on context. There's a case of like spam or not spam. Would you rather have like, if you have a spam filter in your email, would you rather have an important email classified as spam, or a spam email that just like came into your inbox because your computer or your email service system thought it wasn't spam, right?
Those are some great examples, by the way.
Oh, thank you, thank you. These are common examples. I did not come up with these, but yeah. So it's really important to think about when you're trying to solve a problem or like make predictions on something. It's important to think about what are the implications of making type 1 and type 2 errors, and therefore in most cases you generally want to lean towards one more than the other. So yeah, any questions, any overall questions? Because this is the last slide. Well, very cool. On Thursday, we'll be elaborating a lot more on the things that I like touched on very briefly. As you can see, there's statistical power, which is that beta, effect sizes as well. And then we'll have some ANOVA stuff, which is very cool. It's a variance analysis. But yeah, if there are no questions, all right. If there are no questions, I will see you all at your one-on-ones and see you all back at study group on Thursday. Good night, everybody.
All right, good night. Thank you, Ish.